running?
We are running. All right. So test 2 will be out, or will happen next week. Test 2, test 1 was only 15%. That's one of the many reasons why I think midterms are just so pointless, because you've only turned in, at the time, 4 problem sets and a 15% test. So it's roughly, at best, 20%. So there's a lot more involved. Test 2 is 20%. The format of the test is going to be the same. 25 multiple choice, for a total of 50 points, 1 appetizer problem for a total of 5 points, and then 3 15-point problems for a total of 45. What we're going to do is, we're pretty much done with the new material for test 2, so we're now in kind of review mode. What we're going to do is, today on the 13th, and then on the 18th, I think that's the dates, we're doing review. There will be no review session on Wednesday night. Just as kind of an announcement, I'm going to be at the volleyball game Wednesday night as the guest faculty coach. So we're guaranteed to win because my kids don't lose. The other thing, to those who are in Wednesday's 5 o'clock and 7 o'clock labs, I'm not going to be there, but there will be a guest TA who will remain nameless until that time occurs. So you'll all still go to lab. If anybody sees me at the game, we could talk about the test, I guess. So on the 13th and the 18th, today and next Tuesday, we're going to review. The appetizer, of course, will be the right-hand rule game. And then for the 3 problems, it will be torque bar, it will be rotation, alpha may not equal 0, or alpha will equal to 0. The one that isn't done on test 2 will be on the final. So test 2, if you get an alpha equaling 0 on the test, you know that alpha equaling 0 will not be on the final as a problem. Then the last one will be Atwood's machine, of course. Why? Because we always do Atwood's machines. But in this case, it will not be with motion, it will be with energy. There will be friction. I know, ooh, friction. But that information, it'll be the same thing. No equations of motion allowed. So that's it. Right now, what I tend to talk to the class prior to the second test about the progress of the class. I've seen the homework scores, I've seen the test scores, I've kind of seen the averages start to come out. What I've done is I've worked through Blackboard. I've updated the spreadsheet so that cumulative scores are now available, and they are with the plus minus letter grades. So you can take a look at Blackboard and see what your at moment score is. Now granted, it doesn't include half the homework, it doesn't include test 2, 3 and the final, but it does give you an indication of how things are going. After test 2, then things will start to level out, sort themselves out, and we can figure it out. Right now, the class average is an 81, which is pretty much, it's going to be the average for the test. 81 is right now is a B. If you take a look at I'm just going to go down to B minus. 92 is the lowest A minus is an 88, B plus lowest is an 84, then 80, then 76. So the class average is a straight up B, which is good. It's a little bit on the high side, but it's not too much that it would make me panic. What I'm gonna do is, just so you all know, I graduated from a different undergraduate university, a university that believed on curving, harsh curving. There were times where I got a 40 out of 100 and they said that was a B. And I was like, yeah, I got a 40. And then other times I got an 88 and I was told that was a C. And I was like, no, how dare you? So I'm a big believer in the curve. However, my change is, I know how OCD you all are. I do not curve down. Because if I started curving down, oh, the fun we could have. But I know that you all would be on various rooftops threatening to throw yourselves off. So we don't do that. We curve up. Now, on the first test, I don't necessarily say it's the final curve, but the current curve on test 1 is a 0. There will be no bonuses on test 1. However, at the end of the semester, I may choose to curve it up just a little bit. That's the sausage making that I talked about at the beginning of the semester. Test 2, in my opinion, is going to be a little bit harder than test 1. Test 1 was merely a way just to get you guys used to taking a physics test. We were just going through the motions, the basic materials and stuff like that. And with test 2, we now have all the material from test 1 to build upon. So now I'm gonna kind of build on it. And just so you know how considerate I am, doesn't look like there's 160 people in the room, because that's the total enrollment. I understand that sorority, or the rush week is, now first off, my opinion, the rushy is not P&Ms. I mean, just come on. That just makes it politically correct, and I can't stand that. But in the fall, for the fall classes, I wait for one announcement. When is rush week? And then I avoid it. And so that's why the test is the following week. Just as I set my spring tests to the schedule of the baseball team so that I get to go to all the games. So in the fall, it's all about you. In the spring, it's all about me. So there's balance in that. So I'm just saying that I understand your plight. I understand that not everyone is here because you are, many of you are only on 2-3 hours sleep, and I understand that. But test 2 is going to be a little bit harder than test 1, primarily because we're dealing with more material that depends on test 1 material. So we need to, it's not like, all right, we're done with test 1, we can forget about it. You gotta keep up with it. So as the first, we're gonna go do a quick example. I'm going to draw on the board, or on this overhead, right-hand rule game. And I want you to write this down on your sheet of paper. And what we're gonna do is, I'm gonna take this sheet of paper away, and then I want you to do the test that I give you on the board. The letters never have to be in any particular order. So I'll give you about 20 seconds to write that down, and then we'll do the right-hand rule game. This is pretty much like what we're going to do on the test on next Thursday. Because you will not have the benefit of an overhead projector at the test. All right, we got that? Let me write down the going once, going twice, it's gone. Now, okay, so we have 5 right-hand rule problems. Now, how you orient this paper is up to you. So you can hold it like this, you can hold it like this, you can hold it like this, you can hold it like that. It doesn't really matter. The one thing that does matter is you do not change positions of the paper in the middle of you trying to calculate. So if you go B, C, you're doing it wrong. So keep that sheet of paper in the same orientation while you're doing the problem. Yeah, you can turn around like that as long as you keep it like that. So A cross B is what? C. All right. Now, a couple things we need to remember about this course. If I say A cross B, the answer is not. I much more appreciate that the answer that you would say is, you know what the answer is? Answer, I taught. And say it with conviction. I much rather appreciate wrong with conviction than right with uncertainty. So A cross B is C. So you just align, A to me is that way. First vector, fingers out, palm out. B is to me is that way. So A cross B, that's the second vector. Thumb naturally points in the direction of the third vector, which is C. Next, E cross F. Wow. E cross B is not F.
E cross F.
I thought I said E cross B. Oh. What did you oh, hold on. It helps if the professor would actually bother to read the problem. E cross F is what? B, correct. B cross C. Never trust the old man. I know. The coffee has not had its effect yet. B cross C. It's A. Next. Do we see A? Who's confused? I hear confusion.
How do you do B?
B cross C. So over here, we're holding out our paper like this. B is this way. C is up. So that points to the right, which is what? A. Huh? All right, you want us to do E cross F real quick? E is into the page. F is that way. So thumb points forward, which is D. Yeah, good. I can't hear you because of the other people. Yes. Number 2, E cross F. Now I'm going to hold the paper like you have it on the desk. E is towards the ground. F is that way. So E, F, thumb points forward, which if your paper is like this, is in the direction of B. 2, we're still doing 2. C cross D, number 4. C, if I hold it out of the page, C, D is towards the back of the room, which means that it points that way, which is A. And then for the last one, F cross D, F across your chest, D to the back of the room, out of the page of C. So A cross B, E cross F, B cross C, C cross D. That's that. Now, one of the things about the test that I should warn you guys about, we caught a few writing down answers on the test itself and not including it in the scratch work. The test clearly states that we do not grade material that's been written on the test itself. We only grade the Scantron and we only grade the scratch paper. The biggest source of error the entire year is the right-hand rule game, because people just write that stuff down right on the test and we don't look at it. So be sure to put it on the paper. It's not going to go on the Scantron, it'll go right on the test. Or it's in the scratch work for the test. All right. So there's still the homework. As always, we will be doing a tutorial at 1 o'clock Friday in Bishop's main auditorium. It's like 2:00 something, I don't know. But if you have any more questions about the right-hand rule, I have office hours from 9:30 to 11:30ish, and then of course tutorial from 1 to 3. All right, so next. Now with rotation, it could be done in one of 2 different ways. Either alpha is equaling 0 or alpha will not equal 0. If it's an alpha not equaling 0, most likely you'll see a symbol that looks like this. If it's alpha equaling 0, you'll get something, but you won't get that dramatic symbol. You'll get something else. And the something else that I want to talk about is the Fish of Fury. Now, what's really interesting is if you talk to any Eschenberg alumni and you say Fish of Fury, they should just break out in a cold sweat, because the Fish of Fury is the Fish of Fury. It's an angry fish, and we'll figure out why in about a month. In this problem, you've got the Rebel Rod and Reel, copyright 2014. The Rebel Rod and Reel has a mass of 1 kilogram and has a radius of 5 centimeters. So the radius of that wheel is 0.05 meters. And you have 5 meters of line cast off the Rebel Rod and Reel. Now this is the picture of the fish of fury. Isn't it frightening? There's little shark fins and stuff. So the fish of fury catches the bait, which is just a big, I don't know, bulldog head. And the fish of fury moves to the right with a velocity of 15 meters per second. Now the Rebel rod and reel, if you read the box, has 100 meters of line, which means if 5 meters have been cast out, you got 95 meters left. The velocity is constant. So this fish grabs onto the line, moves to the right at 15 meters per second, and the velocity is constant. So if the velocity is constant, first question, what is the linear acceleration of the fish? It's 0. Why is that? The velocity is constant. A is dv dt, so dv dt is 0 because that's the definition of constant for velocity. So the acceleration is 0. How long does it take till the line runs out? So this is kind of a one-dimensional motion problem. If the fish starts at 5 meters and the line runs out at 100 meters, you could say that x naught is equal to 5 and x final is equal to 100. It's a very simple one-dimensional motion problem. So x is equal to x naught plus v naught t plus 1/2 at squared. Acceleration is 0. I'm looking for t, so x minus x naught equals v naught t, or x minus x naught over t is equal to v naught. X final 100, x initial 5, t is, oh no, I'm looking for t. So these are reversed, v naught and t, and that makes it 15. So what's 95 divided by 15? 6.3 repeating. So it takes 6.33 seconds for this thing to run out of line. So we have the time. Now, one of the things that you could ask yourselves is, what is circumference? What's the circumference of the Rebel rod and reel? Well, by definition, the circumference is 2 pi r. So this is 2 times pi times 0.05, and that gives me a circumference of what? Ooh, that's interesting. Pi divided by 10. All right. So the circumference is pi divided by 10, or 0.314 meters. So the circumference is 0.314 meters. How many turns did the reel make? So if it turns once every 0.314 meters, and it let out 95 meters of thread because 5 meters was already out, this means that the number of turns is the distance divided by the circumference. The distance was 95 meters. The circumference was 0.314 meters. And that gives us, yeah, you're already getting bit rot. 302.4 turns. So just by rounding 2 or 3 times, we're already starting to get a difference of about a percentage point. So it'll start adding up quick. Now that we know how many turns it made, if we know how many turns it made and we know how long it took to make those turns, we know the period. So the total time divided by the number of turns is the period. The total time, 6.33, on and on and on. Number of turns, 302.4. And we get a total time of 2.09 times 10 to the negative 2 seconds. Or 20 milliseconds is real, or 21 milliseconds really. And if you have period, you can get the frequency. So 1 over 2.09 times 10 to the negative 2, or 47.7 hertz. Now, in testing situations, we are kind of forgiving about the little bit of bit rot that goes into this. If you're off by a percentage point or 2, as long as you got the thing set up, we're fine with it. If you're off by 40, 50%, we know you did something wrong, and so that's when we start investigating. Question? Okay. Now that we know the frequency, and really, what am I doing with this problem? I'm exploring the space. With the Rebel Rod and Reel and the Fish of Fury problem, it's more of an exploration in your knowledge of what's going on in rotation. If I know frequency, I know omega. Omega is 2 pi f. And as a reassurance, yes, all of these equations will be listed in the equation sheet part of the test. It's just that it's your choice to figure out how to use it. So 2 pi 47.7 is 300 radians per second. And I got 300.0000158. So even I'm a little bit rounding. So the radian, the angular velocity is 300 radians per second. Now, this is, the other way that we can confirm this is V is equal to omega R. If omega is 300 and then R is 0.05, what do we get? We get 15 meters per second. So in a roundabout way, we could have discovered omega right off the bat, but instead we went through all this procedure. So once again, in physics, there are several different ways of doing this stuff. There is no one singular linear way for solutions. Say that again?
What was the variable you were trying to find for that problem, or all of them?
We're trying to find all of them. I mean, really, I would have to say find A of the fish, find time, find frequency, find period, find circumference, find et cetera, et cetera, et cetera. So really, we're just going through a long list of things.
Would the circumference always, no, would the number of turns always be the distance over circumference?
Say that
The
again.
number of turns, would it always be?
Yes.
Distance over?
The distance that the line let out divided by the circumference, yes. Now here's an interesting question. What's alpha? Say it with confidence. Fill the room.
0.
It's 0. Let's find out why. Omega is V over R. Does V change? Does V change in this? No, it does not. Does R change? No. So if V doesn't change and R doesn't change, what can we say about omega? It's constant. Omega is constant. So d omega dt is equal to 0. And what's d omega dt? Alpha. So if this wheel is just moving at a constant angular velocity, the angular acceleration is 0. Okay, next. Give me a moment of inertia of the disk. Well, moment of inertia of the disk is 1/2 mr squared. M is 1. R is 0.05. So the moment of inertia of the disk is 0.025. I have no idea why I needed a calculator. One of the things that I've seen in lab is a lot of students are asking like, well, how do I get the units? What are the units of moment of inertia? And I'm like, well, what's the moment of inertia of the disk? Just give me the equation. And they're like 1/2 mr squared. And I'm like, well, can't you get the variables from that? If M is in kilograms and R is in meters, then the units are kilograms meters squared. Just like in class last night, P is mv, and they wanted to know, well, what are the units for momentum? Well, m is kilograms, velocity is in meters per second. There you go, done. Yes?
So you need to square R. You didn't square the.
Dang it, then I do need a calculator. Yeah. Thank you. Why did it take you so long to bring that up? So, there we go. Now, as you've seen on test 1, if you guys do just what I did, a dumb little math error, we typically take off like 3 points out of 15. It's not a deal breaker. We're not the math department. Oh my goodness. If you want cruelty, go to the math department and take what they call a box test. You write the answer in the box. If it's right, you get full credit. If you drop a sign, you get nothing. That's some horrible stuff. Now, the moment of inertia of the disk, we've determined. Give me angular momentum. I omega. So I is 1.25 times 10 to the negative 3. Omega is 300. And I get 0.375. Now the units, moment of inertia, kilogram meters squared. Units for angular velocity, inverse seconds. So angular momentum is measured in kilograms meters squared per second. And that's probably about as far as I would go in a problem like this. I'd probably cut out a few of these things. This is a little bit long for a problem, but I would shorten it a bit, and then it would be a good test problem. A couple other things that we can do with this. Let's say that there was a 1 gram bug at the edge of the reel. What is the radial? Can't write. What is the radial acceleration of the bug on the disc? Well, radial acceleration is measured as v squared over r. The linear velocity of the at the edge of the disc is the same as the linear velocity of the fish. So it is, what did I say, 15 meters per second? Yeah. So this means it's 15 squared divided by 0.05, which is really big numbers. 4,500 meters per second, or 450 Gs.
AR could be numbers, but alpha is 0.
Excellent question. Alpha is angular acceleration. If you had a wheel that was spinning up, the alpha is non-zero. The angular acceleration of that thing is, this has an alpha. It spins up. This is an alpha equaling 0 if the angular velocity is just at a constant. Now what we're studying is angular acceleration versus radial acceleration. Radial acceleration is based on one simple thing. Is this thing turning? So this thing could be spinning in either direction with any magnitude. And it's equal to non-zero. Radial acceleration is different from angular acceleration. Angular acceleration just lets you know if the object is spinning up or spinning down. Radial acceleration is only dealing with the fact that the velocity vector of the object is changing. So if there is a velocity vector, there must be a radial acceleration vector. They're not related. They're two different terms. They both have acceleration, but angular acceleration just lets you know how quickly omega is changing. Radial acceleration lets you know that there's a linear velocity going on in a circular fashion. They're not associated with each other. You can kind of associate it with the fact that A is v squared over r and v is omega r. And so you can kind of get close, but they're really different parts of the same wheel essentially. Yes. I think that's a fair question to ask on the test. Most likely it will be mentioned. If you don't see the word force mentioned, the letter F, then alpha is safe to be 0. And it's perfectly okay to ask me that question in a test situation.
Basically, if there's velocity, then you have AR.
Yes. If the object is moving, you will have AR.
It's not constant.
Huh?
Not constant velocity.
If you have, oh, good question. If alpha was equaling 0, then AR is constant. If alpha doesn't equal 0, then AR changes. And how is that? If alpha isn't 0, then d omega dt isn't 0. This means omega changes. If omega changes, then V changes. Omega R is equaling V. And if V changes, AR changes. And we get that. So yes, you can't make those assumptions. Or you can't figure it out. Did that answer?
I was talking about the beginning because velocity was constant.
If velocity is constant, you will have a constant radial acceleration.
Yeah, I was asking about the alpha. Yeah.
If V is constant,
It's always gonna be 0.
it's always be 0, yes.
Yeah, so if you were giving us a problem where V wasn't constant, that would be when the alpha wouldn't be 0 and you'd have to.
Alpha could be 0. I could have something constantly spinning like the rebel rod and reel. Then you have a velocity non-zero but an alpha of 0. One of the big things that you can tell that if it's a force, if you see the word force in a circular motion problem, you see the word force, alpha is not 0. Now, the only way that exception torque bars. But you can tell the difference between a torque bar and a rotational motion problem. Torque bars are static. Rotation motions are not. All right. All right, let's go through. Trying to think what else we could do.
So the problem we just did, that was alpha.
Alpha equaling 0. Let's do a problem where alpha isn't 0. So if I have a problem where alpha isn't 0, you see this symbol, you go, oh, alpha is not equaling 0 in this. I know exactly what to do. So R, now I'm going to add a little bit of a twist because these problems need to get spiced up a little bit. So this is a disk The mass of the disc is 50 kilograms. This is a stick. The mass of the stick is 10 kilograms. The radius of the disc is the same as the length of the stick, which will be 2 meters. The force is 500 newtons. Starting from rest, if t is equal to 100 seconds, give me, I want to know moment of inertia total. I want to know alpha. I want to know the number of rotations, and that will be good enough. So I want I numerically, and in a way that's me conceding, hey, here's some numbers, go plug and chug and have fun. The moment of inertia of the system is the moment of inertia of the disc plus the moment of inertia of the stick rotating about one of its edges or one of its tips. The moment of inertia of a disc is 1/2 mass of the disc r squared. The moment of inertia of a stick, since the stick is revolving around not its center of mass but about its edge, is 1/12 ml squared plus mass of the stick d squared. Now what we're using here is the parallel axis theorem. In the parallel axis theorem, the moment of inertia of an object is its original moment of inertia about its center of mass plus md squared. And d is the distance from center of mass to rotation point. So 1/2 mdr squared plus 1/12. The mass of the stick, m sub s, L in this case is the same as r because I set that the stick was at the same length as the disc. So this means it's r squared. The mass of the stick. Now d in this case is the distance from the center of mass to the rotation point. So d in this case is 1/2 r. So what I'm going to do is write this out for another line. 1/2 md r squared plus 1/12 ms r squared plus 1/4 ms r squared. So now I have 1/2 r squared. I'm factoring out a 1/2 and a r squared, md plus 1/6 ms plus 1/2 ms. Now I can plug and chug. 1/2 r is 2, so 2 squared, md 50 plus 1/6 times 10 plus 1/2 times 10. So that's 2 Nope, 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 nope. So I get 113.33333 kilograms meters squared. And so that's determining a moment of inertia of an object which has, it's not a simple geometry, it's a little bit more complex. But remember, just like masses add 2 kilogram mass and a 3 kilogram mass, put them together, what do you got? 5 kilograms. The moments of inertia add up the same way. Yes? I factored out a 1/2 from each of these. Yeah, so 1/2 r squared times md is this. 1/2 r squared times 1/6 ms is this. 1/2 times r squared times 1/2 ms is this. So I simply did factored it out. You don't have to do that part. This?
D equals 1/2 r squared.
Oh, this? Yes, okay. So the stick length is, I kind of flipped it around. This is the center of mass of the stick. The total length of the stick is R. D, what is the definition of D? D is the distance from the center of mass of the stick to the rotation point. So that is D. I should have written this from there to there, not from there to there. But in either case, it doesn't matter, because this distance D is 1/2 R. And that's why I chose a D of 1/2 R.
Dr. Hemsworth,
Yes.
in the before we started doing the factoring, we have 112 ms L squared.
Yeah.
That 112, is that just a given number?
That'll be a given number. I will give you probably we're not going to do spheres. We're not going to deal with big league 3-dimensional objects. But what I will do is disk, 1/2 mr squared, point, mr squared, and stick, 1/12 ml squared.
Okay.
Those will be the 3 given. And then I'll also give you the parallel axis theorem. So I'll also give you,
Like on the equation sheet?
yeah, on the equation sheet, I'll give you this.
Okay.
But you will have to determine what D is. And if you've noticed, there was one person who got together every single test that I've ever given. But that was like a year and a half ago. But what they noticed was, for the first 3 years, I would use simple objects, a disc, a stick, a point, that's it. Now I'm maturing my problems just a little bit, and I'm gonna do like a disc with a stick, a disc with a couple of points. Could be a stick with a point at the end. There was one time I did that. The geometry could change. The procedure never changes. The actual general outline of the procedure is the same.
There's the stick with the disc and a point, you just add it.
Yeah, you just add them together. I mean, if I added a point here, which I'm not, because that would be weird, or that would add an extra layer, it would be this plus mr squared. Mass of the point times r squared. But just like masses, the moments of inertia add the same way. You just add them up. So that is the moment of inertia of the disc with a stick. Now, we've kind of distracted ourselves. Well, what do we need to do now? With a rotation problem, the two equations, sum of the torques is equal to I alpha, and definition torque is force times the radius or distance from the force to the rotation point. So what I can do is one force, one torque. If you have one force, you only have one torque. If you had 5 forces, which we won't do on a test, you would have to sum up 5 torques. So one force, Fr, is your torque, and that is equal to I alpha. Now I know my force was given 500, radius was given 2, I've just solved for moment of inertia, so my alpha is Fr over I. 500 times 2 divided by 113.3, on and on and on and on. So 1,000 divided by that gives me an alpha of 8.824 radians per second. I would even accept inverse second squared or that. Either one's fine. So there's my alpha. And now that I have my alpha, I can determine N by theta equaling theta naught plus omega naught t plus 1/2 alpha t squared. So theta naught is always 0. The initial position of the disk, you just say, that's origin. It started at rest, which means that is 0 as well. I know my alpha, I know my t. T was given to you, 100 seconds. So I can get theta. But theta is equal to 2 pi n. So 2 pi n is equal to 1/2 alpha t squared, or n is 1/2 alpha t squared over 2 pi. So 1/2 8.824 100 squared over 2 pi. So the number is 7,021.5 turns. And so that is the number of turns. So it's, if you get something like this where alpha is non-zero, most likely it will be in the form of find its moment of inertia, give me some information about either A, the number of turns it makes, the force, the angular acceleration, stuff like that. I will endeavor today or tomorrow to put sample tests from previous semesters online so you can take a look at it, and hopefully I can get get an answer key out so that you can compare and contrast. And then on Tuesday, what we're gonna do is we're gonna go over the multiple choice and stuff like that. And then next time, well, since we have 15 minutes, what I'll do is just a simple torque bar problem, and then we've really covered everything on the test. Oh, Atwood. Which do you want to do, Atwood's machine or torque bar?
What do you mean? Yeah.
Both? Well, we only got 15 minutes left, so we'll do torque bar.
Are we doing Atwood's
With energy. We'll do that on Tuesday. And in fact, if you want to talk about Atwood's with energy tomorrow at the tutorial, we can do that too. I envision the tutorial tomorrow to be a combination of homework and test review. I want to know what this mass is. if the tension, let me see, let me put this problem up. The tension in here is 200 newtons. The mass here is 5 kilograms. This distance is R1, that distance is R2, and this distance is R3. The question is, what is mass 2 and what is the force necessary from the fulcrum onto the bar? Now with a problem like this, I would attack it right through the torque. I would choose this as the rotation point. As mentioned on Tuesday, pretty much the safest bet to pick as a rotation point is the fulcrum. So with this, I'm going to choose, I know through observation, this bar is doing nothing, just sitting there. So it's not moving up or down, and more importantly, it's not rotating. It's not rotating about that point. So I have 1, 2, 3 forces. M1G, M2G, and tension. So M1G times its distance to the rotation point, or R1. M2G times its distance, R2. And then its distance, R2 plus R3 times its force, which is T. And I get this. So you sum up the torques is equaling to 0. You write out all the torques, but you leave the signs blank for the temporarily. Then you use the right-hand rule. The force down is to the left. Left, down, thumb up, positive. Because if you get a positive torque, that's, or I'm sorry, an outward torque that's positive, you get an inward torque that's negative. M2G is to the right, down, into the page, or negative. Tension is to the right but up. Right, up, out of the page, positive. So that's how we determine our signs. We're looking for T. M2GR2 minus M1GR1 TR2 plus R3. G, M2R2 minus M1R1 divided by R2 plus R3. So, oh yes, what am I looking for? I'm looking for M2, hold on. Well, see, this is another benefit of the alphabet soup method. I could have given you everything and asked for T. So in the test, I could suddenly decide, well, I'm going to give you M2, find T for me. And so that's how you would do it. But now I need M2. It's right in here. So I'm going to move that over. Find M2. And I get this. 1 over, oh, I need values for R1, R2, and R3. R1 is 1, R2 is 0.5, R3 is 1.5. and I get this. My total answer is 90 kilograms. And that's the mass of 2. So all it is the hard part setting it up. Once you've set it up, you can solve for any of the variables. Yes?
Can you go back over how you make the sums?
Okay. Now what I'll do... Whoa, big. All right. So we use the right-hand rule. If it's coming out of the page, it's positive. If it's going into the page, it's negative. What we do is we always start from the fulcrum and go out to the force. So M1G, fulcrum left. So I have to point this way. The force is down. Thumb points out. Positive. Now for M2G, it's to the right in this case. But the force is also down. Thumb goes into the page, or negative. The tension to the right again. But in this case, it's up. Thumb points out, positive. And that's where the sign comes from.
So you know M2G is to the right, so it's like to the right of.
It's the right of the fulcrum. You pick your rotation point. We've decreed it to be at the fulcrum. And why do I not use F in that equation? Because the distance from the fulcrum to the rotation point, or to F, is 0. 0 times F is 0. I don't worry about it. The last bit. Sum the vertical forces is equal to 0. It's not going to the ceiling. It's not falling down. What? Oh.
Yeah.
Duh, that would help. All right. We're not summing torque, so we don't have to worry about the distance. We're summing forces. F plus T minus M1G minus M2G. I'm looking for F. So M1G plus M2G minus T is equal to F. So this is 5 times 10 plus 90 times 10 minus 200. And that gives us 950, 750. And so we get 750 newtons. And so that's how you do a torque bar problem. All right. Now I have my notes for this afternoon. I use you guys as a warm-up.
So what was the force? You said force is 0?
The net force is 0, but F is 750. All right, that's it. Going once, going twice. See you tomorrow, 1 o'clock.